Hey, guys, it was just about, I know it's actually a minute after 1 here. Hello, everyone, welcome. It's the start of week 5, which means we're about a third of the way through the semester. And I hope you guys are doing well. Hope you had a good weekend and staying on top of everything. A few announcements as we get started here. First of all, so the quizzes, well, I guess I passed back the ones that I could. These are all of the number of people who are not here right now. At the time the class is supposed to start, which is about half the class, not here on time. Speaking of half, I would say the average on this exam was about half. 50%. It's not great. I'm a little bit concerned about it. I did post the solutions, so I'll just encourage you to read those and ask me questions about them if you have any. Yeah, we've got a midterm coming up next week on Thursday. This is sort of a little bit of a tester on that, just to kind of sort of a low impact assessment that I wanted to do. You can close that drape if it's getting in your eyes there. Yeah, the sun is pretty bright right now. So we have our first midterm next week on Thursday. So this is supposed to kind of give you a little bit of an idea, at least about some of the material, not all of it. Yeah, the average was about 50% or so. I just wanna, I don't like to get too emotionally into this kind of stuff, but I've been back for 2 weeks in person. And I am spending a lot of time twiddling my thumbs in my office hours. I have a lot of office hours, of course, and I do have, I would say, 2 or 3 people in here who are really putting a good effort in that I can see anyway. And really trying to, not just kind of check the box of, oh, I did the homework, but to really make sure you're really trying to get it down and to learn it well. But there's some of you who I think could probably stand to put a little more into this. I've taught this past 7 or 8 times, so I sort of know what it takes. And I'm not sure I'm quite getting it from everyone. I just feel like based on kind of the homework scores and the quiz scores recently, that why are my office hours so quiet? I know not everybody loves this material. Of course, the math department, it's not up to me what courses everybody's required to take. The math department's decided that every math major, even if you're not a pure math student, you have to take this class. And so I'm just here to do the best I can to teach it as best as I know how to, and to try to be as available as I can to be a resource for you, to help you to do well. So I'm gonna continue to do that. I will do everything I can, but you are going to have to really put some effort in. Particularly if this doesn't come naturally to you. Once in a while, there'll be a student or two who they don't really need to go to office hours because it just kind of flows for them naturally. But I think for most students, it would really be a good idea to be a little more engaged. And maybe you are, maybe it's happening outside of my sort of little bubble that I live in. But yeah, I just want to really encourage you to step it up a little bit, especially if this quiz was a wake-up call, that you might have to get put a little bit more time into this. A 4-unit course, at a minimum, you're supposed to be spending 8 hours a week outside of class on this. That's kind of the rubric that they give. Now, I don't know, it varies from person to person, but I would say in a class like Math 350, which is so abstract and so technical, it would probably be even a little bit more than that. And then it also depends on where you're at. If you're coming into this with sort of not feeling solid with proofwriting or stuff like that, then you might need to spend even more than 8 hours outside of class, right? And based on what I'm seeing a little bit on some of the quizzes and even on some of the homework, I feel like there are some folks that really need to maybe jack that 8 hours up a little bit higher. So, anyway, not trying to, throw cold water on this at all. I want everybody to do well, of course. That's what my whole goal is, and anything I can do to help that happen, I will do. I was, for example, a little bit surprised as I was looking over the homework that's due tonight. I said, gosh, that's a lot of problems I assigned. I should be having people complaining about it or asking me about it or something, and I just had, nobody said anything to me. I've had a couple people, sort of the same 2 or 3 people coming to my office hours, but I haven't really heard from anybody else. So I don't know how it's going with tonight's homework. As I sent you an email that tonight I cannot have my office hours. I have to leave campus right after my last class because I've got a mountain of exams to grade for my other class. What I think I'll do to sort of semi-bail us out on this is I will come over here and allow you guys during our break today to put down some problems that you might want to see me do. I think, what were the sections? It was 2.1, 2.2, and 2.3. So during the break today, if you want to jot some questions up there, in the second half of our class, maybe we'll have a few minutes and I can give you some hints. In several places in the homework, you can get away with the similarly reasoning. Like if they ask you to prove this, that I think one of them is prove that the supremum of B times capital S is equal to B times the infimum of S. And then they have a second problem to prove that the infimum of B times S is equal to B times the supremum of S. Well, those 2 proofs are all basically the same. You don't need to do them both. You can just do one of those and then just say similarly on the other one. If it's helpful for you to practice it and do them both, sure, go ahead and do that. But I would not be expecting you to more or less regurgitate the same idea twice. So feel free to take a few shortcuts like that when you're working on the homework. But anyway, during the break, you can get a little bit organized with some questions because I won't be able to stick around tonight as of all nights. I just can't stay. I've got to get off of campus. And then there is another homework posted for next week on Tuesday. Definitely recommend you start early, ask questions early, even as early as Thursday. Right, I would normally expect that in a 350 class, that the very next office hour after the assignment is out, there's going to be people coming to ask questions. So you really have to start early on this stuff to get it done on time. And especially with the midterm next week, I think it'd just be good to try to get that homework done. The midterm is on Thursday. So let me just, by the way, I'm just going to make a little schedule here. So the midterm is next week on Thursday, and it covers, so that's February 27th. It covers up through section 3.2, which is actually what we're covering right now. We actually very well might finish it today. So we'll have all the material for the exam covered. I would like to do a review session beforehand. Now, unfortunately, because I have so many classes on Tuesday and Thursday, I'm probably not going to be able to do a review session on Tuesday. I was thinking of doing one on Wednesday, which is the day before the test. Now, you would need to do your part and start studying the weekend before. But if you wanted, I could do, I was thinking of doing a review session on Wednesday. Now, I realize that you guys have other things to do. You might have classes or other issues. What I think I'm going to do is I'm gonna send you guys a doodle poll. Probably, I'll do it this afternoon or this evening. I'll send you a little poll, and I'd like you to just fill it out. And what it's gonna consist of is I'm gonna basically take this Wednesday and I'm gonna create a whole bunch of 2-hour windows, probably going all the way into the evening. Something like that. And I'm probably gonna pick a couple of them. I'll probably pick like whatever the 2 most popular ones are, and I'll have a couple of 2-hour sessions. I will record both of them and send them out to you that same day, obviously, because the test is the next day. But I'll try to do a couple of review sessions on Wednesday next week. So keep your eyes open for that. Meanwhile, there is a sample midterm in Canvas for you to kind of look at. I've got the solutions to that midterm also there. I would try not to look at the solutions though. My advice on how to do this is to try it as a real exam. Probably not yet. I would probably wait till somewhere around next Tuesday or Wednesday or something like that. Try that sample test and then ask me questions or look up the solutions to it. There's also a review packet that just has like information about, oh, here's what you should be able to do for the test. Here are the theorems you need to know, right? The main results, that kind of stuff. So it might be a good idea to start with that. I'd probably start with just sort of the overview. It's only like a page or two, just listing out stuff to look over. And just make sure you've got all those definitions down, all the theorems. I know some of you are working with flashcards, which is really awesome. So just make sure you've got a good set of sort of definitions and theorems down, and then sometime around next Tuesday or Wednesday, when I'm doing the review session, would be a good time to try that sample test. That's just my advice on it. But I will be recording the review session. I probably will pick some times that not everybody can come. I know you have classes on Wednesdays probably. So it'll just be, I'll do the best I can. I mean, honestly, I could go, maybe I'll add some late night spots here too, because I'm up late. It's not a problem for me. And see if I can be of some help. But anyway, any questions about any of that? Okay, great. So anyway, so we've got the homework due tonight. During the break, you can add some problems over here and I'll try to give you some hints on that. Meanwhile, what I'd like to start with is picking up, like I said, we're almost done with section 3.2, which is the last part of what's going to be on next week's test. So I just want to pick up where we left off on Thursday with this. We have the definition of a convergent sequence here, and if it converges, it has to converge to something. So here I've kind of used this notation, the sequence xn converges to x, right? Very easy to write it with that arrow notation. And here's this big symbol heavy definition, right? For all epsilon greater than 0, there exists a natural number n naught such that as long as n is greater than or equal to n naught, meaning that the term, so that n is referring to the terms of the sequence, as long as you are far enough along the sequence, right? So that you're at least in the n naught term or further, that the distance between xn and x is less than that epsilon, right? So the epsilon is sort of a fixed pi. Find this n naught. Okay, so that's kind of what you have to do to prove that a sequence converges directly from the definition. So on next week's homework, which covers 3.1 and 3.2, in 3.1, you're going to mainly be using that definition to prove that things converge or don't converge, right? Because you also have the negation of this, which would be sequences that don't converge, and we did an example of that last Thursday as well. Once you get to the second half of the homework for next week, on this one, you're going to want to use the theorems, such as the one we're about to talk about here, to prove that sequences converge using the various theorems, like this limit theorem here, which is what I've put back on the board from last time. Okay, so just keep that in mind as you're thinking about next week's homework. It's kind of in two parts. The first part is the introduction, where you use the definition to do everything from scratch. And then the second part is where we start building these theorems that we can use. Okay, so let's actually take a look at this theorem again. We did not prove it last time. I'd like to go ahead and make sure that everybody's comfortable with how this would be proven. Okay, so we have two sequences, xn and yn, and imagine that they both converge respectively to x and y. Fair enough, right? So then it turns out that we can add those convergent sequences together, and it will still converge. And no surprise, it will converge to x plus y. Okay, so that's not surprising, right? We would kind of normally expect that. Same thing with multiplication. Xn times yn will converge to x times y. This third one is actually just a special case of the second one, where you have a multiplication, but where one of the sequences is just c, 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 constant value of c all the time, right? So of course, that's going to converge to c times x. And division, if I have a quotient of two sequences, that also works how you would expect it to work, with a little sort of asterisk on that one, that we should make sure that none of the denominators are ever zero. Okay, so that's a fair thing to assume, and as long as we have that, property also goes exactly how you would think it would. Okay, so let's try and prove these a little bit. It's actually, the first part is very easy to prove. After we get past part one, we'll find a little bit of surprises with this proof. So that'll be kind of interesting to see. Okay, so I'm gonna come over here now. And I'm gonna start proving part one. I think that part, I think we can handle straight away. Okay, so we would like to prove that if xn converges to x and yn converges to y, then xn plus yn converges to x plus y. Okay, so anytime you're proving convergence from the definition, you're gonna start with that rubber stamp sentence, which is let epsilon greater than 0 be given. Right, so let epsilon greater than 0 be given. Our job is to come up with an n naught that will work for this sequence xn plus yn. Now, we already know that xn by itself converges, so there's already, by assumption here, there is already an n naught for this sequence. And similarly, the yn converges to y, so there's already an n naught for this sequence. Now, they aren't the same n naught, right? So I'm gonna use a couple of different notations here. So since xn converges to x, I'm gonna say there exists an n1 in the natural numbers. I'm not gonna call it the same n naught because this is not the ultimate n naught that I'm gonna be trying to derive. Such that if n is greater than or equal to n1, then absolute xn minus x is less than, actually, I can put less than anything I want here. Because I'm assuming that xn converges to x, which means that for all epsilon whatsoever, I can find this n naught. Does anybody have an idea what I want to put here? I actually don't want to put epsilon there. Epsilon over 2, exactly. This is going to be an epsilon over 2 right here. Awesome. Okay. You'll see why in a second. If it's not clear to you why I'm dividing by 2, you will see it in a moment as we continue with this proof. I'm going to do something very similar with the yn sequence. So similarly, since yn converges to y, there exists, this time I'm going to call it n2, because again, it might not be the same natural number. We don't know that. Maybe it is, maybe it isn't. Such that if n is greater than or equal to n2, well, then absolute yn minus y is also, same thing, less than epsilon over 2. Okay, and we're going to see in just a second how to put these two epsilon over 2's together. Okay, our job is to come up with an n naught, and I'm wondering if anybody maybe has a proposal for me about what the n naught maybe should be. Because I'm trying to prove right now that statement 1 is true, which means that given the epsilon, I have to come up with an n naught. So this is my challenge. Do you have an idea?
The max of n1.
The max of n1 and n2. Very good. We're going to take the max of those two n. So the idea behind that, guys, actually, whenever you're working with sequences like this, it's always going to be, if you have multiple of them, you're always going to take the max. Okay, wait till the next chapter when we start doing epsilons and deltas, and we'll be taking mins all the time. But for right now, it's always maximums. Why is that? Well, it's because I'm going to assume that my n is greater than or equal to n naught, which will mean that it's greater than both of these. It'll be greater than both of these, right? So we've constructed our n naught, and now I just need to check, does that n naught work with this definition here? So let's check it. Let's assume that n is greater than or equal to n naught. And what I want to do is I want to look at, well, I should say this definition with this sequence, right? So it's going to be absolute of xn plus yn minus x plus y. So we have that difference right there. This is really the big thing we want to calculate here. And any suggestions what I might want to do with that?
Triangle.
I do want to use the triangle inequality. How should I maybe group the terms though? Is there something we should we reorder them somehow maybe first? I put all the x's together and then I put all the y's together because these assumptions individually have only the x's in them and only the y's in them. They're separated. So I'm gonna do that here, guys. I'm gonna do that right here. This is equal to absolute xn minus x plus yn minus y. So that's exactly the way you wanna do it, okay? So you just kind of do it like so, and then we'll take Luis's idea is to now use the triangle inequality. I'm gonna split this up into less than or equal to absolute xn minus x plus absolute yn minus y. And each of these, by assumption, see n is greater than or equal to both the n1 and the n2, because we chose it to be the max, right? So therefore, each of those is less than half of epsilon. This is why you want to use the epsilon over 2. So it adds up to epsilon, and that is what we needed to prove. So a little check here. That's part 1. That's part 1. So far, so good. Make a reasonable amount of sense, I hope. I'm trying. Let's think about, well, we might think that we're just going to jump straight into part 2. It turns out that to prove 2, the second statement, we need a little bit of a preparation for it. Okay, I have to give you a little bit of preliminary results first. So we actually need a quick little side conversation here. So I'm going to tell you what it is. There's a definition that we need to write down, and then a little proposition. So this is definition 3.5 in the book. And it's a pretty easy definition, but we do need to get it written down. And the way that this works is a sequence xn is bounded. A sequence is bounded if there exists a positive real number, I'm going to call it capital B for this definition, a capital B such that absolute xn is always less than or equal to b. This would be for all terms of the sequence, for all n, all little n. Okay, so that's the definition of bounded. So it's a pretty simple idea, guys. Here's your number line. You've got 0, right? And b is maybe here. And if b is there, then of course negative b is over here. And if the absolute value of xn is less than or equal to b, it just means all of your terms have to be inside of this, boundary of plus or minus b. So you have a whole bunch of terms here, right? But they have to all stay kind of close to 0. And that's kind of what bounded means. Something like that. Okay, so a bounded sequence. All right, so that's the definition, and now there's going to be a theorem to go with the definition. So let's write down the theorem here, guys. It is actually proposition 3.2. Again, I'm using the numbers from the book just to help you with doing your studying. You can look it up in the book as well and very easily be able to have it. So here's what the proposition says. If the sequence xn converges, then it is bounded. Then it is bounded. So a convergent sequence has to be bounded. I mean, all of the terms of this sequence are eventually going to get very close to a particular point x, which is fixed somewhere on the real number line. So that means all of those terms are sort of some finite distance away from 0, right? So we could build this b accordingly, right? Now there is an issue that we even though the sequence converges, the first few terms might be wildly spread all over the number line, right? We don't know that. All we know is that as long as we go far enough, as long as n is big enough, then my xn's are somehow controlled to within a certain distance of x, you see. But those first few terms, before we get to the n naught term, we can't say anything about those, right? We don't really know where they could be. So this actually takes a little bit of a proof here. By the way, before I do the proof, just a quick remark. What about the converse of this? This is a classic question a Math 350 class would ask is, since this is if then, does it work the other way? Would a bounded sequence have to converge? I'll give you a hint. If that was true, it would have been stated that way, right? The theorem would have said if and only if it was true. Yeah, the converse is false. And so we'll jot that down. And if something is false, what are we supposed to usually try to do? Give an example, a counterexample. And I bet that we can do that. Let's try to give an example. Can anybody think of a sequence that is bounded but which does not converge? Which one? Sign of n, that is actually true. It's not the one I had in mind, but I will point this out. Xn equals sine of n. Okay, so this is a weird, we haven't really thought much about something like a trig function in this class. So sine of 1, sine of 2, sine of 3. It is definitely bounded because we all know that sine stays between -1 and +1. The fact that it does not converge, however, is maybe not obvious. Okay, it turns out that this does not converge, and therefore it is a good counterexample. And I'm just going to say see homework. It's actually not until section 3.3, so it's a little bit. This will be after the exam. We'll have a homework problem where we actually prove that. So we can actually prove that the sine of n doesn't converge. Can anybody think of another example? Thank you, Amber. That was a good example. Can anybody think of another one that we've actually already looked at in this class? There we go. That's the one that I was thinking of. Xn equals, by the way, you only need one counterexample, but I like to give multiple of them if there's some good examples. -1 to the n. We actually proved on Thursday last week that this does not converge. And yet it obviously is bounded because it just bounces from +1 to -1 to +1 to -1. So I'll just say see notes from February 13th, I think it was. Yeah, so that was the example that we actually proved that that sequence doesn't converge by using this definition. We did it directly from scratch. Yeah, okay, so the converse is not true, but that's okay. The statement is still going to be important for us to know. A convergent sequence is always bounded. Let's now write down the proof of this. So let's prove this. This is not very long. We'll see if I can squeeze it into this amount of space over here. I always get optimistic about that, but let's just assume, since Xn converges, let's just assume that Xn converges to X again. So we'll just assume that it converges. Because it converges, then everything about the right-hand side of this definition is true right now. And so that means for all epsilon, blah, blah, blah. So I get to pick whatever epsilon I want. I'm gonna pick one, and it actually doesn't matter which one you pick, but I'm gonna just pick a number that will be really nice, which is just 1. So I'm going to let epsilon equal 1, because then from that definition, by definition, there exists already an n naught in the natural numbers such that if n is greater than or equal to n naught, absolute of xn minus x is less than whatever my epsilon was, which I said was 1. So this is just, and again, the picture is not part of the proof here, but guys, but what we're really just saying is that we can make an interval between x minus 1 and x plus 1, and as long as we go past the first n naught terms, right, which we cannot apply this statement to, all of the subsequent terms are all in here. And you can kind of see that if they're all within there, they're kind of bounded. And that's the intuition behind it, that they're all kind of bounded. Okay, so we've got that. And so thus, I think I do need a little more room. I'm just gonna erase this little homework help thing over here. I'll put it back up when we get to our break in a little while. But let's just come over here so I have enough room to kind of finish this. I don't want to try to squeeze it in too tightly. So thus, if n is greater than or equal to n naught, so I'm just gonna look only at the n's that are greater than or equal to n naught. What you guys will notice is that, yeah, I can talk about how big xn is. I mean, I'm really trying to prove that xn is bounded. So I would like to have some number I can put over here, right? So let's just see if we can say anything about this. So this is what we have to do, right? To match that definition, I have to put a bound on this guy, right? And I'm going to do it right now. There's this very common trick. You've already seen this a couple times, guys. This in this chapter where you kind of add and subtract the same thing inside of absolute value bars. So here I'm just going to subtract x and add x with the plan that I want to kind of use my triangle inequality again. Okay, so this is kind of something that will become second nature to you soon enough, because we do see this quite often. So you split it apart using that triangle inequality, right? And see, the point is that this first term is less than 1, right? So this becomes less than 1 plus absolute x. So is that my b? Is that my b? I've got my absolute xn less than, what's less than or equal to 1 plus absolute x. That look like that will be my b? There's just one thing wrong with it. It's not a big deal, but this inequality is only for the n's that are at least as big as n naught. Remember I was talking at the beginning, the first few terms of this sequence could be all over the place, right? They could be very far away from the origin. And so this little calculation here tells me nothing about x1 or x2 or x3 or x4. It only tells me about x and naught and beyond. So that's great for all of the sort of what we call the tail of the sequence, the terms past a certain point. But the first few terms we have not addressed here. But the point is that there will be only finitely many of those missing from this constraint. Because n naught might be, let's just say n naught is 17. That means for all of the terms except for the first 16 terms, this would be a great b to use for that definition. But I've got 16 x's that we cannot use this for because they aren't big enough to match n naught. Well, fine, then there's only 16 additional things that we have to take into account, and here is how we actually fix that. Here's what we're actually going to do. We're going to set b to be a max of, so let's just grab the absolute values of those first few terms that are giving us all the trouble. So I'm going to go from x1 to x2 to x3, all the way up to the last subscript before this takes over. Can you guys all read that here? This is n naught minus 1. Right? That's the last subscript that is for which this calculation does not apply. But after that point, we can then go with 1 plus absolute x. We need to put that in there as well as the way to bound all of the subsequent terms. So this is the correct choice of b. Incidentally, guys, you can only take a max and have it make sense if there are finitely many things listed. So you might wonder, why didn't you just start off by saying max of x1, x2, x3, x4, dot, dot, dot? Like, why couldn't I have just done that? Well, the thing is the dot, dot, dot goes on forever. And so your capital B can never really be determined if you're continually trying to find a max of an infinite list. Well, this is not an infinite list anymore. This is 16 outliers, right, or n naught minus 1 outliers, followed by a sort of an overarching upper bound for the remainder of the sequence. So putting that all together, you have a B value that would be well defined. It would certainly make sense. It's obviously going to be greater than 0 because you're taking the max of a bunch of positive numbers, right? So this is certainly a reasonable B to assume. And so then the absolute value of xn is less than or equal to V, not just for the n's that are greater than or equal to n naught, but for all n's. So that is what we need to assume there. Okay, so that's the proof of that proposition. Convergent sequences have to be bounded. It's kind of intuitively should be clear, I would say. Should be kind of intuitively clear because you have only finitely many terms that you cannot control. And after you get past n naught, well, after n naught happens, all of the rest of the terms are controllable. Yeah, they all get controlled by that limit of absolute x. Okay, so any questions on that? So far, so good? Yay, okay, if we're doing okay with that, now I'm ready to come back and prove part 2 of this theorem, and you're gonna see why we need that proposition. Okay, we do need that proposition here. So now let's come back to the main limit theorems that we are looking at, and I'd like to try to give you guys the proof of part 2. Let's see if this is gonna make some sense, okay? I want to prove that the sequence xn times yn converges to xy. Again, I got my definition. Again, I start off with my rubber stamp. Let epsilon greater than 0 be given. That's how we always get these things rolling. And I'm going to maybe come over here to the side this time and do a little bit of scratch. You saw me do this last week on some of these, and this is another proof where having a little side scratch might be helpful. Remember, what is it we really want to show? We want to show that xn minus yn, xn yn, just xn yn minus xy. We want that to be less than epsilon. I mean, that's ultimately what we're going to need to do to prove number 2. Okay, but I think to sort of see where this is going to come from, it helps to kind of put it over here on the scratch side of things. And once again, what I'm going to do here is that same trick. I'm going to add and subtract something in the middle that is exactly the same thing. So I'm going to take this thing, I've got my xn, yn, and then I'm going to subtract xn times y. And then I'm going to add it right back in, xn times y, and then minus xy. So we're just going to stick 2 terms in the middle that are actually just canceling each other out. They're actually just the same thing. Okay, so we have that. This thing here, let me just do another if and only if here. This thing is set up so that you can do some factoring now. So you see the first 2 terms both have an xn, and you can factor yn minus y from that. And then the last 2 terms both have a y, so you can factor xn minus x from that. So you just pull the common factors out of the first 2 terms and pull the common factors out of the second 2 terms. Okay, you guys with me? Okay, so my goal is actually going to be, if I need to make this whole thing less than epsilon, I'm going to want to use the triangle inequality again. And I'm going to want to sort of make absolute of xn times yn minus y. I'm going to need to make that one less than, I'm going to use this epsilon over 2 idea again. I'm going to kind of split these into 2 parts. And I also want the other one to be less than epsilon over 2. So I'm going to try to get both of the 2 parts of this thing to be less than epsilon. Okay. So actually, I'm going to erase that. You don't have to erase it. It's okay. I want to ask you a question. So if I want to use the triangle inequality, this thing here is obviously less than or equal to what? This one times yn minus y plus this one. So all of that, right? So basically this one and this one. So my question is that an if and only if step right there? So if this is true, would this have to be true? And is it also true that if this one was true, then this one would be true? That's kind of what my question is. Which of these two things is smaller? Is it this one or is it this one? This is smaller, right? Right, this is smaller. So we all know, right, absolute value. Let me just throw some totally different letters up here for a moment. Right, the one where everything is inside the big absolute value bars is the smaller one. So would you agree that if the larger one is less than epsilon, then the smaller one would have to be less than epsilon too? But not the other way around. This only goes backwards. Now, the good news is I only need it to go backwards. I'm ultimately going to be trying to prove that this is the conclusion that I want to get. I am going to be reversing the steps of my scratch work, right? Remember? So we're going to do that by going backwards through this scratch work. This is a step that only works backwards. In other words, if this one is true, there's no reason to know that this one is true. Because after all, you're replacing this with something bigger. As soon as you replace it with something bigger, maybe it's not less than epsilon anymore. All right, that would be the possible issue with that. So just be careful. This is the first time we've seen this where we have something that's not totally reversible, but it's okay. It goes in the direction that we would like it to go. Okay, and I'm going to, well, as long as I'm just doing backwards arrows now, I'll just do one more that's only backwards, which is what I wrote before, which is absolute xn times yn minus y should be less than epsilon over 2, and absolute of xn minus x times y less than epsilon over 2. So if both of those individual terms are less than epsilon over 2, then again, going backwards, if I add them together, the result will be less than epsilon. Okay, so this is kind of what I want. This is kind of what I want. I'm going to go a little bit more. I'm still on my blue marker. That means I'm still doing scratch work here. I told you this proof is a little trickier than just everything totally straightforward. We have to play a little careful with this. So I'm going to take each of these two things individually. I got a big and between them. I'm going to work on both of them individually. On the first one, I have absolute yn minus y less than, what is it, epsilon over 2 absolute xn. So I'm going to divide the xn underneath here. Okay, and I'm going to do something similar on the second one, absolute xn minus x less than epsilon over 2 absolute y. And again, the reason I'm doing that is because, of course, we already know that xn converges to x, and we already know that yn converges to y, which means that these differences, xn minus x and yn minus y, we have some control over. So I basically, this is like my new epsilon, and there will be an n naught here, except I'm going to call it n1. And then there will be an n naught here, but I'm going to call it n2. And then we're going to take a max again. So that part of the proof really is working the same. Let's see if we can write this down. Okay, I'm going to try to write it down now. Our job is to find an n naught. And I'm going to find an n1. Maybe I'll start with this one and then an n2 here. Okay, so let's see if we can do that. But I have a little bit of a problem before I do that, right? I do know that xn converges to x, which means for all epsilon, this would be my epsilon now, right? Okay, but I do have a little bit of a concern because y could be 0. So This is good thing it's in my scratch work, because if this was in my main proof, I would be screaming right now that I could be dividing by 0 here, which would be a problem. But we can fix that by just kind of replacing the absolute value of y with the absolute value of y plus 1. Just make that denominator a little bit bigger, and that'll take care of it. So let's do that. So since now I'm back on the main proof. Now I'm back ready for the main proof. Since xn converges to x, right, there exists an n1 in the natural numbers such that if n is greater than or equal to n1, absolute xn minus x is less than anything we want to write down, right? Or anything greater than 0 that we want to write down. Okay, this epsilon was arbitrary. So I get to put anything here that I want, and I already have sort of cheated with my scratch work. I know what I want. I want epsilon over 2 times, I really wanted absolute value of y, but it won't hurt me. It won't hurt me if I do a little plus 1 on the bottom there, because that makes sure that I'm never going to divide by 0. And it also makes this fraction smaller, right? Making it smaller can only help us in this situation in terms of trying to make this whole thing less than epsilon. Okay? I mean, so my point sort of that you can be thinking about here is that this is going to be less than epsilon over 2. It's going to be less than epsilon over 2. It's got a little extra denominator here, but that's perfectly okay. Now I'd like to do the same thing with the yn sequence. I would like to find an n2 such that if n is greater than or equal to n2, absolute yn minus y is less than. Okay, so now here we have another issue. On this one, we also have an issue. If the xn is 0, we will have the same problem that we would if the y was 0. And we have another problem actually here. Other problem with this is that n is not a fixed value. This is not just like a single number. There's an x1, there's an x2, there's an x3. It's like, well, which of the xn's am I talking about here? Which term of the sequence is this? This needs to be a fixed value here. I can't have it sort of in terms of some roaming variable of n, right? So this is where we need the proposition. You notice we haven't used it yet. We need this proposition that tells us that the yn sequence, which converges, is bounded, and so is the xn sequence. They're both bounded. So here's the way we're going to handle that. Since xn converges to x, I'm still using the same xn sequence again, right? That sequence xn is bounded. So what does that mean? Sorry, that's by proposition 3. Let's just add that to the notes here. So this is by the proposition 3.2. So the sequence xn is bounded. So there exists a b greater than 0, right? There's a positive real number b, that's the definition of bounded, such that absolute xn is less than or equal to b for all natural numbers n. So that's the definition of bounded. So you know what I'm going to do? I'm going to replace this absolute xn here with something larger, namely b, because that only makes the fraction smaller. Making the fraction smaller, just like we did with this term, we made it smaller by doing the plus 1 here. I'm going to make this one smaller too by replacing xn with b. Yeah, exactly. So now let's go ahead and do that. Since yn converges to y, there exists an n2 in the natural numbers such that if n is greater than or equal to n2, absolute of yn minus y is less than, again, I can put anything I want over here and I'll have a correct statement. I'm going to choose to put epsilon over two B. Yeah, epsilon over two B. So that's perfectly fine. Okay? I need a little more room to finish my proof. I think I'll come over here to do that. Takes a little bit of work, doesn't it? But we have the N1 and the N2 in our hands. So what is my N naught going to be? One more time. The maximum, exactly. We're gonna take the max of N1 and N2. Come right over here to do that. Let N naught equal the max of N1 and N2. Okay, so we'll take the max. It's always the max, right? In this chapter, it's always a max. You don't even have to break a sweat for that. It's just always going to be the max of the previous n's that you have. And now I'm just going to check that that n naught works. So let's assume that n is greater than or equal to n naught, right? So now I'm going on to the definition. I'm going to assume that n is greater than or equal to n naught, and I'm going to look at this absolute value here, right? So then what do we have? Then we have absolute xn, yn minus xy. This is what we want to look at. We want this to be less than epsilon. Okay, but what I'm basically going to do is I'm going to replace this with, we're just going to follow the scratch work, but I'm actually going to write this out. So we're going to replace this with xn, yn minus xny plus xny minus xy. So I'm literally just gonna, I think just because it's just complicated enough, I'm just gonna go ahead and show all of my steps here. This one is equal to absolute of xn times the quantity yn minus y plus the quantity xn minus x times y. That's just factoring. Just factoring it. Now I'm going to use the triangle inequality. You knew that was coming. I'm going to rewrite this as less than or equal to absolute xn times absolute yn minus y plus absolute xn minus x times absolute y. Like that. And what do we know? N naught is greater than or equal to both n1 and n2. So we have bounds. We have bounds now on the absolute differences of the xn sequence and the yn sequence. So I'm going to plug those in here. So on this one, I've got a less than here, right? I've got absolute xn times, let's see, what do we have for yn minus y? Oh, that was epsilon over 2b. So the yn minus y is less than epsilon over 2b. And then on the second term, we have epsilon over 2 times the quantity absolute y plus 1 times absolute y. Hi guys, we would like to have epsilon over 2 for both of these terms. Look at this first part. The first part has an xn on top and a b on the bottom. Well, good news is the top is smaller than the bottom, right? So xn is less than b. That means the numerator is smaller than the denominator if we sort of just ignore the epsilon over 2. So we have epsilon over 2 times something that can be replaced with 1, essentially, right? And then on the second term, same thing, guys. I have an epsilon over 2 times, look at your numerator, look at your denominator. Right? The denominator is bigger than the numerator. So as a fraction, this thing is less than 1. If I replace it with 1, then I get this larger epsilon over 2 here. And now adding those two together, finally, we can celebrate the epsilon that we achieve in the last step. That's it. That's basically it. Okay. So this one is a little tricky because what you want to bound the, like when we did part 1 of the proof, I just put epsilon over 2 here and I put epsilon over 2 here, and that was all I had to do. I didn't have to deal with these denominators here. But on this proof we did. We had to replace absolute y with something that we knew wouldn't be 0. And we had to replace absolute xn with something that's not a function of n, right? We needed a fixed number for that. So we replaced it with b. Is kind of how this is working. What do you think? Any questions on that? It's not so bad. Okay, part 3 of this theorem is just a special case of part 2, so we don't really have to prove anything. So let me just write this down for part 3. This is just a special case of 2 where we just, for the y sub n sequence, we just make it equal to c for all n. Obviously, that sequence converges for all n. And so there's nothing more that we really have to say about that. Other than that, okay? And then finally, for number 4, I think I'm gonna omit this one for now. It's basically dealing with quotients. So I'll just say omitted, maybe I'll do it in the review session or something. It's not that bad, but you do have to deal with the fractions and stuff. The first thing you can do is you can assume that the numerator is just 1. You can just do this as 1 over yn and prove that it converges to 1 over y, because then you can apply the multiplication property to get the xn into the numerator and get the x into the numerator here. So you actually can, it's enough, let's just add that here. It is enough to show that the sequence 1 over yn converges to 1 over y. We don't actually have to deal with the x in the numerator, because you can always apply the multiplication principle to get the x, which is part 2 that we've already proven. Yeah, so we can get away with that, but I will omit it for now. I think it's maybe not that big of a deal to do that. So, okay. Let me do one more thing before we take a little break, just so we have something else that we can chew on while we're thinking about a break here. Actually, let me state it over here. I want to state and prove the famous squeeze theorem that you probably learned about in calculus. So as we get further into the semester, guys, more and more of the things we do will be theorems that you will remember and recognize the names of, because we're getting into more and more of the calculus as we go. And these are, you know, the results that you probably took for granted in your lower division calculus classes, you know, because the class is usually 90% engineers and they don't care about why any of these things are true. They're just going to take the theorem and use it. But I know that you guys would like to hopefully understand why these things are true. So let's put down another theorem here. This is the famous squeeze theorem. Actually, there's more than one squeeze theorem, but this is the one for sequences, okay? Which is what we're talking about right now. So let's do this, guys. Let's let xn, the sequence xn, the sequence yn, and the sequence zn, let's let these be sequences with xn less than or equal to yn less than or equal to zn. Let's say for all n. For all natural numbers n. Okay. Then if xn converges to x and zn converges to the same x. So if the smallest sequence converges to x and the biggest sequence converges to x, then the one in the middle, which is y sub n, also has to converge to x. It gets squeezed to the same limit value, right? It gets squeezed down to the same value. That's kind of the idea behind this one, okay? So if xn converges and zn converges to the same value, but the sequences are arranged in this, I guess, monotone increasing order, as we'll talk about later, then the sequence in the middle has to converge to the same thing. So this is a very short proof. This is much less involved than the one we proved a moment ago. So I can write this down in just a small space here. surprising that it's so short, but it is. It's actually very short. I would like to prove this. I always like to look, what am I trying to prove? This is what I'm trying to prove, and it involves convergence of a sequence, which means what's the first sentence of my proof going to be? Thank you. Let epsilon greater than 0 be given. I like it. Okay. Let epsilon greater than 0 be given. So because xn converges to x and zn converges to x is already assumed, we can already find an n1 and an n2 for both of those, right? So we can find n1 in the natural numbers such that if n is greater than or equal to n1, then absolute xn minus x is less than whatever I want to put here, which actually it turns out you don't have to even be clever on this one. You can just go with the same epsilon, okay? And then similarly, you'll see in a second, it doesn't matter. Similarly, we can find a natural number n2 such that if n is greater than or equal to n2, then absolute Zn minus Z is less than epsilon. Oh, I wish I had a little bit more room here. I want to add sort of a different phrasing of this, of both of these inequalities here, because this is going to actually help us with this. Do you guys remember the little result that if, let me just scribble it over here. Do you remember this little result of absolute x is less than c? That really just means what about x?
It's between negative c and c.
Yeah, exactly. It's between negative c and c, right? And that's exactly right. So I'm actually going to want to use that. So in this case, it's negative epsilon less than xn minus x less than epsilon. And same thing here, negative epsilon less than zn minus x less than epsilon. Do you see my typo in my proof, by the way? I just saw a typo in my proof.
Yeah, it converges to x, not z.
There is no z. This is supposed to be zn minus x. Sorry about that. Sometimes I make a mistake just on purpose to see if anybody's paying attention. So there we go. We've got an x in both places here. And that's what we should have written down. Okay. Great. Okay, so now does somebody want to tell me what my n naught is going to be? The maximum of n1 and n2, right? It's always the maximum. In this chapter, we will always be doing maxes. Don't worry, the mins won't be getting left out. In the next chapter, it's going to be mins all over the place. But for right now, it's maxes. We're going to take the max of those, and I'm going to claim that that is our n naught that we need. Let's assume now that n is greater than or equal to n naught. And I'm going to try to convince you that absolute yn minus x is still less than epsilon, right? So this is just a one-line calculation here. So then negative epsilon. Okay, so here's where I'm going to use the negative. But so basically, these statements here, guys, that I'm circling right now, this is how you remove absolute value bars from your expression, right? If I have absolute value of x and I just want to know something about x, I can remove those absolute value bars by creating this statement here. So that's basically what I've done. So let's go ahead and start feeding this in here, guys. Negative epsilon is going to be less than, I think it's going to be xn minus x. And that is in turn, see, xn is less than yn less than or equal to yn minus x, which is less than or equal to zn minus x, and zn minus x is less than epsilon. So you have all of that, just making a big chain. It's just a big chain. But look right here in the middle, guys, is the thing you wanna look at. That expression is controlled between plus and minus epsilon, right? So that means that the absolute difference of those two things is less than epsilon. That's what we needed to prove. That's what we needed to prove. So the squeeze theorem is pretty easy to prove there. And then I can give you a really quick example of how you would apply it. And then we'll take a little break, but it's easy to give an example here. The one I like to do for the squeeze theorem is, I like to do trig functions. Because trig functions are hard to work with directly using the definition of convergence. But it's very easy to squeeze them between things that we know. So just to give a quick example of this. Let's let, I'm gonna call the sequence yn for this example so that it fits the role of the yn in my squeeze theorem here. I'm gonna let yn be the sequence sine of n over n. And I'm going to claim that the sequence yn converges to 0. So if you see trig functions in a sequence that you're trying to prove something about, I highly recommend using or thinking about the squeeze theorem at least. I would not want to have to prove directly that this converges to, how would you do it directly? Oh, well, we would take sine of n minus what it's supposed to converge to. We would set it less than epsilon and try to solve for n. Right, which would ultimately be the n naught. Right, and it worked great the other day when we had nice expressions here. We could use the Archimedean principle and it all worked out beautifully. But this has an n in 2 different places that I don't really know a good way to sort of isolate the n here. So I would not want to have to do this, right? It's just the algebra of that would be quite a hill to climb. But what we can do instead is we can just simply note, so for the proof, what we can do here, guys, is we can just simply note that we have 0 is less than or equal to, I'm going to use the absolute value of y sub n. Okay, just so it's definitely positive. And that is in turn less than or equal to 1 over n. So you see the xn, yn, and cn right here, yeah? This is just a constant, 0 converging to 0. It's okay, we'll just draw arrows on our solution here. I don't mind that. And then 1 over n also converges to 0. That's, by the way, something you can just use. 1 over n, I mean, you set it less than epsilon and you do a reciprocal and solve for n, use the Archimedean principle. We don't need to keep reproving this. I'm telling you that because next week's homework, this fact that 1 over n converges to 0 will be used multiple times, and it'll be nice to not have to continue to prove it every single time you see it. So you can use this as a, this may be used, I'll say freely. You can just use it freely whenever you want. There's no problem with that. Anyway, so there's your xn converging to 0. Here's your zn converging to 0. So that means the one in the middle has to converge to 0. So by the squeeze theorem, the absolute value of yn converges to 0. And one of the homework problems that you're going to do, I'm just going to say by homework number 6, so this will be for next week. One of the things that you're going to prove is if the absolute value of a sequence converges, then the original sequence itself converges. So therefore, yn itself converges to 0. And that's what we were claiming. Okay, so by homework number 6, I forget which problem it is exactly. It's not a hard problem to do, to prove it. If the absolute value of a bunch of numbers is going to 0, then the numbers themselves have to be going to 0. Yeah, that seems reasonable. Okay, great. Questions on the squeeze theorem or this little example of it? For now? All right, guys, I think I've talked long enough. Why don't we take a 10-minute break? During the break, if you've got questions from the homework that's due tonight, this is going to be your last chance to ask me anything, because as I said, I don't have office hours tonight. So we'll take a 10-minute break and then I'll try to help you with the homework if you need it. Thanks. Some problems today. Alex is over here. And Kosi. Are you too far away from me?
Thank you.
You're welcome.
Any homework for questions you're gonna write down?
Tonight,
Any homework problems you want to get?
you know, it's really- Lost the entire class.
Huh?
We lost the entire class. What's going on?
We should talk to Jake.
Sitting there staring at a screen full of Japanese. You doing short office hours afterwards?
Pardon me?
You doing short office hours?
A short office hour, but it may be swamped with the other classes. They're gonna test it for, so we'll see. I don't know what kind of Zoom will be downstairs, but could be like that. I will try. Try my
It's
best.
busy down there.
Pardon me?
Pretty busy down there.
Did you just go down?
Yeah. I
Is
need-
it all my students?
I needed it. No,
Oh, because they haven't tested.
it's just, well, I think one table is. The other table is just already yours.
I see, I see. Gotcha. All right, guys, I think most folks should hopefully be back by now. I'm gonna go ahead and get started again here. Before I take a look at that homework, I wanted to do one more example here to go with the notes of what we were just talking about. Let's suppose I asked you to prove that this sequence here, 2n squared plus 5n minus 7 over 3n squared plus 8. Suppose I ask you to prove that it converges to 2/3. And there will be several like this on next week's assignment. But you would hate to do this. I'll write this down, but this is bad. You do not want to do it this way, which is to say, oh, well, I'll go back to the definition. I need to make xn, which is this thing, minus x, which is 2/3. I need to make that less than epsilon. You would hate to start with that and then say, okay, now I gotta solve for n. And so, because I want to get my n naught, right? That this would be very hard, right? This is hard to do on an example like this because, you know, this is kind of a messy algebraic expression and you may not be able to algebraically solve for an n naught here. So we have a much better approach now that we can do by using those limit theorems, which is the whole purpose of that 4-part theorem that we started with today. What we can do, guys, and here's the way you do these. Maybe you remember, you might even remember this from when you took your calculus courses before. When you have something like this, what you want to do is start by just dividing through the entire expression, all of the terms on the top and the bottom, by whatever the largest power of n is that you see. So I see an n squared here, and that's the highest power of n that I see. So what you can do is just divide everything through by n squared. So you end up making a bunch of fractions. So this is how you're going to want to do the homework in section 3.2 next week, is to just do this little manipulation. Divide every single thing on the top and the bottom gets divided by n squared. You see that? Okay. And now, you know, this is a quotient. So if I can figure out what the numerator converges to, and if I can separately figure out what the denominator converges to, then by part 4 of our limit theorems, the limit of this quotient would just be the quotient of those two individual limits. So in other words, what I'm saying is, you can basically break this up into numerator calculation and denominator calculation. If I focus only on the numerator, I can ask, well, what is the limit of the numerator? Or what is the, convergence value of the numerator? Well, I can view this as three sequences added together. And if they all individually converge, then the limit of that will be just what, summing up what they converge to. Well, 2 just converges to 2, it's a constant. 5 over n converges to 0, you're allowed to use that little fun fact. This is a freebie, so here you've got 1 over n converging to 0, you're multiplying it by 5. Then I think part 3 says if you have a constant, just multiply the constant by whatever the limit is, that would be 0. And the same thing here, if 1 over n converges to 0, then you sure as well would bet that 1 over n squared will do the same thing. It's just the product of 1 over n with itself, right? So that's also converging to 0, right? And then you go to the denominator and you say, okay, well, what's the limit of the denominator? Well, the denominator consists of two things added together. Find their individual limits and add them up. The limit of 3 is 3. The limit of 8 over n squared is 0. And so there you go, that's your answer, this equals 2/3, and all you have to say here is, by the limit theorems. Technically, it's theorem 3.2, but again, you don't need to know theorem numbers, I don't expect you to memorize those, I should say theorems, there's several different results that we are using there. But that would be, isn't that a much nicer proof? We worked really hard in the first half of the class to prove those 4 parts of that limit theorem. So we want to use them, right? And here's an example of how you can use that. By the way, you cannot do those limit theorems unless you have divided through by n squared everywhere first. If you say, well, I'm just gonna work with this, then you have a problem. Because what's this? What's 2n squared converge to? Doesn't converge. Actually, later on, we're gonna define something called converging to infinity. There'll be a definition for that. We haven't done it yet, so I would have to say this doesn't converge, this doesn't converge, that converges to 7, but I don't know what all of that could collectively adds up to. At best, you would come up and say, well, that's infinity on top, and then that's infinity on the bottom, and now you're left with something that's an indeterminate form, right? So now you're getting into all of these subtle points of limit theory that we haven't even gone over yet. So I would not want you to manipulate this one. That's why it's actually better to just divide through. And this is literally an equal sign, right? I'm literally just dividing the numerator through by n squared and the denominator. So this is just basic algebra to change it from this form to this form. But in terms of trying to use my limit theorems, this is the form you want. So that every single individual thing converges to some finite value that you can apply those theorems to. So it is important that you do that. Does that make a little sense? Okay, fantastic. Anything else on that example? I'll let you try a couple of those on next week's homework. Nothing tricky about it. Just kind of follow your same principles as what I just showed you right here. So hopefully that'll be helpful. Okay, let me see here. A couple of problems ended up on that board over there. Let me get the homework out that is due for tonight. Let me start with 2.2, number 7. I may not solve these fully, but I'll try to give some hints here just to help people out a little bit. Number 7 says A and B are subsets of R. By the way, I never used to go over homework during class in Math 350 before. They made it into a 4-unit class now, so I have a little more time to do this, right? So hopefully this will be helpful for you guys. So it says show that the supremum of A union B is just the max of the supremum of A and the supremum of B. And the second part is the infimum of A union B is the min of the infimum of A and the infimum of B. So you have a similar statement there, okay? So this is an example of what I was talking about at the start of class today about this homework. Yeah, there's a lot of problems here. But this one, you don't need to do it unless you've already done it, in which case you've got a double dose of practice. You can just say, this is similar. I will not expect you to have written that one out. It's basically turning inequalities around and just flipping the whole definition over and kind of working at it that way. Okay, so we're not gonna really talk about this, okay? Actually, what you really should do, if you're not comfortable with this, is try it on your own later. Like use it as something to study for your midterm. But in terms of like finishing it up by tonight, you don't have to do that, okay? So let's just work on the first one, okay? Now, the maximum of these two supremums, we don't know which one is going to be the max, but you can see that this is a very symmetric problem. The A and the B are playing completely identical roles. There's no preference of one over the other. There's no information about one that's not true about the other. So what we can do here, guys, is we can assume without loss of generality. This is also going to clean up our proof a little bit. This is going to make our proof nicer. Assume without loss of generality that the supremum of, which one do you want to be bigger, A or B? Does anybody care?
A.
A. So let's assume without loss of generality that the supremum of A is at least as big as the supremum of B, which would mean that the max of these two would be sup of A. Okay, and then let's let alpha be the supremum of A. And I'll just use beta for the supremum of B. So we can just use those notations just to save a little bit of writing. Can somebody remind me in a minute what these other problems were? 2.2 number 8 and 2.3 number 4. Okay, I got to erase. A little more room here. Okay, so and by the way, guys, you're welcome to write this down exactly as is, and then everybody's going to get this one right on the homework. At least that's the plan. Yeah, so the claim is that the supremum of A union B is equal to alpha. That's gonna be the claim. Because we're assuming without loss of generality that alpha is the bigger number, okay? So guys, now we're in this situation where we're trying to prove what the supremum of a set is. There's two parts to it, right? This template that I gave you last week, right? The first part is you've got to prove that alpha is an upper bound for A union B. And then you have to show as a second part that if gamma was an upper bound for A union B, that alpha was less than or equal to gamma. In other words, that alpha is really the least upper bound, which is what supremum means, right? So remember, supremum just means least upper bound. So to prove this, guys, you absolutely have to do this in two parts. I guarantee you on next Thursday's midterm, there will be either a supremum or an infimum proof where you have to do these two steps. This is a big deal. I want everybody to be able to do this. So let's get the proof here. I'm actually even going to number and label these two parts. So the first part is alpha is an upper bound of A union B. I'm going to try to show that much. Now, how do I prove that? Well, I have to pick something in A union B, arbitrary. Okay, so let's do this. Let's do the proof of this part. Let's let X be in A union B. So just grab something random out of A union B. And my job is going to be to show that alpha is greater than or equal to X, because it's supposed to be an upper bound for everything in this union. Right. Now, there's two cases here, right? There's two cases. So either X is in A or X is in B. So if X is in A, so start with that. That's one possibility. I won't label it out as two cases. You could if you wanted to, but I'm just going to keep flowing my my write-up here together. So if X is in A, then would you agree that X is already going to have to be less than or equal to alpha? Because what is alpha? Alpha is the supremum of A, specifically alpha is an upper bound of A. It's greater than or equal to everything in A, right? So then then I'm just gonna say x is less than or equal to alpha. And we could give a little reason here. This would be since alpha is an upper bound of A. Great. So there you go. Now, that's not the only case. We're not ready to finish step one yet. I have another case, which is what if x is in B? So if x is in B, then could we similarly say that x is less than or equal to beta? Here we said x is less than or equal to alpha. If x is in B, then x would be less than or equal to whatever the supremum of B is, which is beta. I'll just say similarly, I won't write out the whole text again. X is less than or equal to beta, but how do we know about, how do alpha and beta compare with each other? We're assuming, right, that alpha is greater than or equal to beta. So actually, if alpha is greater than or equal to beta and beta is greater than or equal to x, then alpha is greater than or equal to x. In other words, x is less than or equal to alpha, since we assumed that well, beta was less than or equal to alpha. We assumed that the supremum of A was the bigger of the two numbers. So regardless of where x lives in this union, whether it lives in A or whether it lives in B, doesn't matter. The end of the day, we end up concluding in both cases that x is less than or equal to alpha. And so that means that alpha is an upper bound. It is greater than or equal to everything in capital A. Right, so we can just wrap that up. We're pretty much done. I'll just say, so alpha is an upper bound of A union B. Okay, so that's the first part. If you didn't write that last sentence down, I would be okay with it. Because honestly, this last sentence is really just restating what I've underlined here that I'm trying to prove. Okay, let me come over here so I can do the second part. We're not done yet. Now we have to pull out this gamma that could be some other upper bound for A union B. So for part two of this proof, let me just come over here for part two. Here's where I'm going to show that alpha is the least. Now we're focusing on the least part, the least upper bound of A union B. It is an upper bound. We've got that part established. It is an upper bound. Now I want it to be the least. Yeah, I want it to be the least one. So this is where, again, we pull out this gamma. So let's assume gamma is an upper bound of A union B. We'll assume we have this gamma in our hands. That is an upper bound of the union. And what I would like to show is that alpha is less than or equal to gamma. Because it's supposed to be the least upper bound. So comparing the two upper bounds, alpha should be less than or equal to gamma. Right. Okay, well guys, if gamma is greater than or equal to everything in the union, then do you agree that it's also greater than or equal to everything in A itself and in B itself separately, right? So actually, this means that gamma is an upper bound of A, just of A itself. If you're greater than or equal to everything in the union, then you're obviously greater than or equal to everything in that set. Well, wait a minute. Gamma is an upper bound for A, but what was the least upper bound of A? Alpha. Oh my gosh, I think we're done, right? Because comparing the two upper bounds, so I'll just say here, since alpha was the least upper bound of A, in other words, the supremum of A, then alpha is actually less than or equal to gamma. We actually don't need to use the set B here. We don't need to bring in the beta on this second part at all. That's all we have to do right there. Okay, so this is a check. This is exactly what we wanted here, and that proves part two. Everybody with that? It's always a two-step part. It's first show that it's an upper bound, then bring in some other gamma, and show that your upper bound is better than gamma. That's basically how it works. This clear? Everybody okay? Tim, are you okay with this? You look a little, you sure? Good, okay, perfect. Anybody else have a question on this? Ayushi? It's just because we did this without loss of generality thing, which meant that the alpha was already going to be the larger of the two upper bounds, and so that was the only one that we really needed. I mean, I could have said gamma is an upper bound for B, therefore gamma is, therefore beta is less than or equal to gamma, and that would have been true. But beta being less than or equal to gamma does not guarantee that alpha is less than or equal to gamma, because alpha is larger than beta. So as soon as you change beta to something larger, this comes into doubt. So this wouldn't really be helpful so much in the second part. Yeah, exactly. Okay, clear enough? Any other questions on that? Okay, so I like these problems. There's a couple others in the homework. There's also the one with the inf of A plus B equals inf of A plus inf of B. I think that's like the very last problem on section 2.3. For that, you can also just model it straight off of last week's proof, because I did the supremum one in class last week. So you're basically just using that as a guide to help you with that second proof. So yes, a word to the wise. I like these problems. Let's see, there was also, I'm sorry? Number 8. Yes, show that, is it 3:40?
Yes, 2 points.
2:40. Oh, gosh, okay, I forgot that clock is off by an
Yeah, you can talk for 3 hours.
hour. Sometimes it probably feels like it. Okay, yeah. Anyway, I've only got 10 minutes, so let me try to get right to the chase here. Show that a non-empty finite subset of R contains both a max and a min. Again, you don't need to do the min, just do the max and say the min is similar. So show that if A is a non-empty set with a finite as a subset of R, I'll just write the word finite next to it there. So A is a finite non-empty set, then A has a max and a min element. Okay. You might remember we had the well ordering principle. This was an axiom that said that the natural numbers, any non-empty subset of the natural numbers, even if it wasn't finite, we assumed there would always be a minimum element. So this is kind of related to that, but here we're assuming the subset is finite. In the case of the well ordering principle, we're sort of just assuming that it is finite. So, or sorry, we're assuming that it has a minimum element, even if it's not finite. Anyway, so for this one, you can just say similar. You don't need to show this part because it's almost identical to the max part. And there is a hint here. It says use induction. So it says use induction, and I want to use induction on the size of the set. How big is the set, right? So let's assume that A is the set little a1, little a2, little a3, and so on up to little a sub n. Let's say there's n elements. If n is 1, so you probably remember from your proofs of induction from Math 280 that you have to do a base case and then you have to do an induction step, right? So if n is 1, that would just mean that A is the set of A1, just a singleton, and that is itself a maximum element if that's the only element that you have, right? So A1 is the maximum element of A. If you're the only team in the tournament, you can claim you got first place, right? So that's pretty nice. Anyway, so that's that. Now let's go to the induction step. And what I want to do for this is I'm going to assume the statement is true, if the size of A is, let's say, n or less, we can use strong induction, although we don't really need to. So I'll assume that for all sets of size n or lower, that the statement is already true, and then I'm just going to consider a new set, I'm gonna call it B, and B is just gonna have A1, A2, up to AN, and then AN plus one. So you make a new set that has n plus one elements in it. And you'd like to prove that there's a maximum element here as well. Now, in this notation, note that A is a subset of B. You can kind of see I've written it out that way, but A only has n elements in it, which means that the induction assumption applies to A. So A, which is just this much of it, already has a maximum element. Okay, so since the size of A is equal to n here, A has a maximum element. So you just look at that list and it has some maximum element. Let's just say it's A sub I. For some I with I going from 1 to n. So somewhere in those first n subscripts, you'll find one that is denoting your maximum element. Okay? And so then the only question is that still the maximum of B? And the answer is, it might be, depending on this new element, A sub n plus 1, and you literally just have to compare them now, right? So you just have to say, so if A sub I is less than or equal to A sub n plus 1, then A sub n plus 1 is the new maximum. So then in that case, you have identified the maximum of B. It would be that new element, A sub n plus 1. Otherwise, the only other possibility is that A sub I itself is still the maximum of B. You just have two cases there, and in either case, you are able to show that there is a maximum element to this set of size n plus 1. And that's how induction works. Yeah. Make a little bit of sense? Questions there at all? Okay, great. If not, then there was one more, which I think I have just enough time to do. It doesn't take very long, which is number 4 on section 223. And I like this problem a lot. It's kind of a clever little problem. It just says to show that the irrational numbers, which you can just imagine removing the rationals from the reals, is dense in R. So another good vocabulary term for your flashcards we talked about last week. Denseness just means if you make any interval in the real number line, you can find an irrational number in there, right? And this one also comes with a hint. The hint here is that the square root of 2 is irrational. So keep that in mind. We'll use that in a minute. But let's consider, let's just assume that X and Y are real numbers with X less than Y. This one I might draw a little number line sort of picture on the side. Remember, the picture is not the proof, but the picture just might help me think about it for a minute. So here's X and here's Y, and I've got that interval, right? I've made this interval, and what do I have to prove? I have to prove that I can find an irrational number in here. Now, we know that the square root of 2 is irrational. They gave us that hint, so we're going to probably try to use that. But of course, we don't know if the square root of 2 is actually in here. So it's going to take a little bit of work to bring it into play. Are there any other dense subsets of R that we already know that we can at least identify something that's in that interval to begin with? Just the rationals, right? The rationals are actually dense in R, and it turns out I do need to use that, right? So let's just remember that. So since Q is dense in R. Does anybody remember the theorem number for that?
Just had it.
Shoot, oh, here it is, I found it, theorem 2.2.
Yeah.
So if anybody needs to look that up in the future, you can refer to theorem 2.2. We did it last week, right? Since Q is dense in R, what's that mean? That just means there exists a little Q in this interval. So I'll just say with X less than Q less than 1. Okay, so that is a rational number somewhere in here. We don't really know where. Maybe it's right here. Just add it to my picture for a minute. But I want to produce an irrational number that is in that interval. And somehow the square root of 2 is supposed to have something to do with that. So does anybody have an idea what we could do?
Maybe let Q equal 2 and then.
We don't get to dictate what this is, because we don't know what it is. So it's just some rational number. I think you had another homework problem that said something about if you add a rational number to an irrational number, you get an irrational number. So I could take this rational number, add it to the square root of 2, and it would become irrational, right? The only problem is, what if adding the square root of 2 to Q moves it way over here? That could happen. Right now it's not in the interval anymore. So what we really want to do is we want to add something to Q that involves the square root of 2, but isn't too much, right? Well, you might imagine maybe we could take that radical 2 and give it a big old denominator to kind of shrink it down so that it's small enough that this distance, right? That distance, by the way, is y minus q. Let's just do a little scratch here, guys. Right, we would like whatever we're gonna add here, let's say n, to be, we would like this guy to still be less than y. So we started with something that was in the interval. We want to add something irrational to it, but not too big, right? Whatever we add to Q, we want it to be such that the result, this will be irrational, right? But we want to make sure it's still inside the interval. So, you know what? Basically, let me rewrite this, sorry. What we really want is Q plus radical 2 over n to be less than y. Let me subtract the Q to the other side. This is all just scratch. Only if y minus q, right? That's what we're looking at. Can we solve that for n? We sure can, right? We sure can. This is if and only if. Let's flip it over. N over radical 2 is greater than 1 over y minus q. And one more step here, I'm going to multiply through by the square root of 2. So n is greater than square root of 2 over y minus q. Can we find a natural number greater than that? Sure, by the, one more time? The Archimedean principle, right? Exactly. So now let's go back to our main proof here, guys. By the AP. Right? I'm almost out of time. I'm basically done. Basically giving you a solution. There exists a natural number n such that n is greater than square root of 2 over y minus q. Now we're just going to retrace the scratch. Going a little bit fast because I am down to like a matter of seconds to go here. Retrace the scratch. And what you get is that, okay, sure, x is still less than q plus radical 2 over n, which is now less than y. And this guy here, q plus square root of 2 over n, is not in q. This would be by problem, what problem was that? Problem 1 from
1 on 2.1.
2.1, number 1, yeah, something like that. So you know that that's still irrational. And so you're good to go. You have found an irrational number that's between x and y. That good? Okay. I think I just barely finished. I'm gonna go ahead and stop for now right there. On Thursday, we'll do some group work on sequencers to practice that. And we'll also finish section 3.2. So I think we're making good progress. I will be downstairs briefly. I think I am not gonna have my office hours tonight, but I will be downstairs for 20 to 30 minutes if there's any last questions before I have to disappear until Thursday. I will see you guys again soon. Thanks for being here.